This lesson is on the product and quotient theorems using complex numbers, assuming that those complex numbers are written in trigonometric form. We assume that you already have had experience in converting complex numbers from their standard form into the trigonometric form and vice versa. So if you have not done that, you'll want to have that lesson before pursuing this one. The way we're going to start this lesson is to look at multiplying complex numbers by the old technique that you probably learned in algebra, where you use the FOIL process. And then from that, we're going to look at how we can get that same product perhaps a little bit easier using the trig form. We are to multiply the following complex numbers. 3 times the square root of 3 over 2 plus 3 halves I is to be multiplied times 1 minus the square root of 3 times I. Now, in the standard format, the way that we multiply is to simply use the FOIL process like you use with binomials. So, first of all, we would multiply the first term here times the first term here. So 1 times 3 square root 3 over 2 gives me 3 square root 3 over 2. Then we will do the outside product, so 3 square root 3 over 2 times negative square root 3i. Notice that the square root 3 times this square root 3 produces a 3 times this 3 makes 9 halves, and it'll be negative, so minus 9 halves times I. Then we'll do the inside product, 3 halves I times 1 is a plus 3 halves I. And then finally, the last two terms, when we multiply these, we get a negative 3 times the square root of 3 over 2 times I squared. Then recall that I squared is equivalent to negative 1, isn't it? So this negative 1 that's going to replace I squared will change this to a plus sign. Okay, so let's rewrite here. We have 3 square root 3 over 2. Let's go ahead and add these two middle terms together. Negative 9 halves I plus 3 halves I gives us a negative 6 halves I. Let me write it in that form right now. Negative 6 halves I. We'll reduce that in a second. As I said, replacing I squared with negative 1 is going to change that to a plus 3 square root 3 over 2. Okay? So 3 square root 3 over 2 plus 3 square root 3 over 2 is going to give us 3 square root 3, and then we'll reduce this minus 3 times I. Okay? Now, what I want to do, once that I have this product, we're going to convert this answer into trigonometric form so that we can see what happens here in just a second. So recall, for trigonometric form, first we're going to calculate R by doing the square root of x squared plus y squared. Okay? So for this particular problem, this would be x. If we square this, we'll have 9 times 3 is 27. Plus, if we square the y, if we square negative 3, we get a plus 9. So r is the square root of 36, which is 6. Okay? And then recall that the tangent of theta is our y, which is negative 3, over our x, 3 square root 3. We can reduce this to negative 1 over the square root of 3. Now remember, as we select the value of theta, we're going to think about the quadrant. If x is positive and y is negative, think x positive, y negative, we're going to be in quadrant 4. Okay? So, let's think about our special angles. If you have your 30-60 triangle, if the tangent is 1 over the square root of 3, that's the 30-degree angle, but using it as a reference in quadrant 4, you would come around, have 30 degrees left, so that would be theta is 330 degrees. So this is equivalent to 6 CIS 330 degrees. I want us to remember what we have here in terms of the trig form. We're going to look at multiplying these same two numbers. Notice multiply, we have the same exact numbers here, but this says first change our numbers to trig form. Okay, so let's look at this first number. And this one's going to be a little bit of work, but we're doing this to develop our theorem, okay? So r is going to be the square root of x squared plus y squared. If I square this, I have 9 times 3 is 27 over 4. Plus, if I square this, I have 9 over 4. So that gives me what? 36 over 4, which is 9. And the square root of 9 is 3. Okay? My tangent theta is my y, 3/2, over my x, 3 square root 3 over 2. So if we invert and multiply, we have 2 over 3 square root 3 here. The 2's cancel, the 3's cancel, and it simplifies to 1 over the square root of 3. Since x and y are both positive, we're in quadrant 1. So the angle we saw a minute ago that has a tangent of 1 over the square root of 3 is 30 degrees. So 30 degrees. So this first number in trig form is 3 CIS 30 degrees. That's my first number. Okay? Now, let's look at converting this second number. Okay, my r is going to be the square root of, if I square x, I get 1, plus, if I square my y, I get 3. So that is the square root of 4, which is 2. Okay? For this problem, the tangent of theta, my y is negative square root 3 over my x is 1. Think about this, when x is positive, y is negative, so that's going to be quadrant 4. Now notice here, it's square root 3 over 1, so my reference is going to be 60 degrees. So if I go to quadrant 4 with a reference of 60, theta is going to be 300 degrees. So this second number in trig form is 2 CIS 300 degrees. Okay? Now, I want to remind you, a while ago, when we multiplied these numbers and we took the product, in trig form, the product is 6 CIS 330 degrees. Now, let's look at what we have right here. Notice I can get the 6 by multiplying this r times this r. And then I have my CIS, and notice the 330 degrees is the sum of 30 degrees and 300 degrees. Okay? Now, I have simply demonstrated to you with a specific example what happens when we multiply two complex numbers that are written in trig form. I have not really proved the theorem, but I have demonstrated it. Let's take a look at what that theorem says. The product of two complex numbers in trigonometric form is given by. Now let's notice here we're doing a product. My first number, R1 CIS theta 1. So I have R1 times cosine theta 1 plus I sine theta 1. Remember that notation. Times R2 times cosine theta 2 plus I sine theta 2. If I'm multiplying two numbers in trig form, first of all, I multiply the two r values, r1 times r2. And then I have my cosine plus I sine thing, and notice I add the two angles. That turns out to be much easier, for the most part, than doing that old FOIL process. Now, let's look at an example here. Find the product, and then write the product in standard form. Now you'll notice these numbers are in the trigonometric form, so doing the product is going to be very simple. I'm going to multiply my two r's. 6 times 4 gives me 24. And then I'm going to have my cosine plus I sine, that I'll abbreviate CIS. I'm going to add my two angles. So 330 degrees plus 210 degrees gives me 540 degrees when I add them. Okay, 24 CIS 540 degrees. Now you will notice that this angle is more than one revolution, isn't it? So let's take away 360 degrees to get that revolution out of there. because 540 degrees is equivalent in terms of our trig functions as 180. I've simply taken my revolution off. Okay? Now, this turns out to be very simple. Think about what we have here. Let me remind you, this is saying 24 times the cosine of 180 degrees plus I times the sine of 180 degrees. Okay? Now, think about 180 degrees or pi. What's happening with the cosine right there? If you remember, the cosine is -1. And what about the sine of 180 degrees? That's 0, isn't it? The sine of pi is 0. So we simply have here -1 plus 0 times I. So 24 times -1 is -24. Now, that product was very simple to get using the trig form, and then as it turned out, our angle was fairly simple also to give us that solution. Here's another problem. Find the product and write the product in standard form. 1.3 times cosine plus I sine 17 degrees times 7.2 cosine plus I sine 194 degrees. Now, I'm going to use my calculator to help me to do this multiplication since it's not as easy to do in my head. So first of all, I'll multiply the r's. 1.3 times 7.2. That gives me 9.36. Okay, then I'm going to write my cosine plus I sine abbreviation, and then I'm going to add my angles. 17 degrees plus 194 degrees is 211 degrees. Okay, now again, recall this means I have 9.36 times the cosine of 211 degrees plus I times the sine of 211 degrees. Since 211 degrees is not one of my special angles, I'm going to use my calculator to get those approximate values. So I will be distributing this 9.36 as I do this. I'm going to do 9.36 times the cosine of 211. Be sure as you do this that your calculator is set for degrees so that you don't get an incorrect solution. Okay, so because of the decimal places here, we're going to be rounding off. I have -8.02. I think I'll just keep hundreds here, -8.02. Okay, now I'm going to do 9.36 times the sine of 211 times I. So 9.36 times the sine of 211 gives me a -4.82 times I. So I have done the product and written the product in standard form very simply using this product theorem. Now you'll notice here I have trig form, but instead of these angles being given in degrees, they're given in radians. But if you notice also, all it has asked for here is the product. It has not asked me to write this in standard form. So as it turns out, this is going to be fairly simple. Again, I'll multiply my r's. 4 times 3 gives me 12. And then I'm going to do my cosine plus I sine. Recall that the next step is to add my angles. Well, I'm going to come down here. I have pi over 3, and I want to add 5 pi over 9. Now, I need a common denominator to add, don't I? So I'm going to take this fraction and multiply both by 3. So I'll have 3 pi over 9 plus 5 pi over 9. And adding numerators, I get 8 pi over 9. So I have 12 CIS 8 pi over 9. Now, if I had been asked for the standard form, I would want to perhaps convert my calculator to radians, and I could do it with a calculator. Of course, you could also see about a reference angle here and see if that was one of your special angles or not. I don't believe it is. But in any case, we could get standard form were we ask for that. Now, we have seen multiplying complex numbers when they're in the trigonometric form is really pretty simple. Now we want to talk about division of complex numbers. I don't know if you recall the process when the numbers are in rectangular form on getting a quotient, but it sometimes can be pretty difficult. So we're going to do one of those and sort of develop the quotient theorem much like we did the product theorem. Let's take a look. Find the quotient of 3 square root 3 over 2 plus 3 halves I divided by 1 minus the square root of 3I. Now in the old rectangular format, here's the way we did this. We wrote 3 square root 3 over 2 plus 3 halves I, and we showed the division by drawing a fraction bar. We're dividing by 1 minus the square root of 3I. Okay? Once we had it in this format, if you recall, what we did is sort of like rationalizing a denominator. We had to multiply by the complex conjugate of the denominator, 1 plus. Notice they're alike except for this sign. So we had to multiply numerator and denominator by this complex conjugate. Okay, now that's going to require foiling both of these places. Okay, well let's do this one here. So multiplying 1 times 3 square root 3 over 2, I have 3 square root 3 over 2. My outside product, I'm going to get a 3 times 3 is 9 halves I. My inside product is going to be a plus 3 halves I. And then my last 2 is going to be 3 square root 3 over 2 I squared. Okay. On the bottom, notice because of the conjugates, 1 times 1 is 1. Notice the outside product is going to be a positive square root 3 times I. The inside is going to be a minus square root 3 times I, so those are going to cancel out. And then I will get a minus square root 3 times square root 3 gives me 3I squared. Okay? So have you followed the FOIL part? Now, recall each of these I squareds we're going to replace with -1. So let's do a little simplifying. I have 3 square root 3 over 2. Adding these two, 9 halves plus 3 halves is 12 halves or 6I. And replacing this with a -1 makes this minus 3 square root 3 over 2. In the denominator, this will change this to a plus, so I have 1 plus 3. Okay, well notice in the numerator, these cancel out. So I have 6I over 4, and I can reduce dividing by 2. I get 3 halves I. I'm going to write it in that format, 3 halves I. Now, much like we did with the product, I want to convert this 3 halves I to the trig form so that we can see what happens here. Okay, so 3 halves I, remember, is like 0 plus 3 halves I. So for R, I've got the square root of 0 squared is 0 plus 3 halves squared is 9 fourths. That's going to be the square root of 9 fourths, which is 3 halves. Can I do tangent theta? Well, y is 3 halves, but x is 0. That's undefined, isn't it? So remember, we think about the graph. 0, 3 halves would be my ordered pair. My vector would be going up on the y-axis, so my angle is 90 degrees. So 3 halves I is 3 halves CIS 90 degrees. Okay, again, we're going to come back to this answer here in a second when we look at this next example. You'll notice again, I'm using the same numbers. I want 3 square root 3 over 2 plus 3 halves I divided by 1 minus square root 3I after changing these numbers to trig form. Okay, so let's do our conversions first of all. Using this one, R is going to be the square root of, if I square this, I have 9 times 3 is 27 over 4, plus if I square 3 halves, I have 9 over 4. That gives me square root of 36 over 4, square root 9, which is 3. The tangent of theta, my y is 3 halves over my x, 3 square root 3 over 2. Okay, I'm going to flip and multiply. We've done this a while ago. 2's cancel, 3's cancel. I get 1 over square root 3. So what is my angle here when we do this? The angle whose tangent is 1 over square root 3. Remember, you can always draw your triangle if you don't remember. That's going to be 30 degrees, isn't it? So my theta is going to be 30 degrees. Notice this is a quadrant 1. Both are positive. So my first number is going to be 3 CIS 30 degrees. Okay? Now, we're going to divide this by this one. So let's find the trig form for this one. R, okay, if I square x, I get 1, plus if I square y, I get 3. So I have the square root of 4, which is 2. And the tangent of theta is my y square root 3 over my x1. I'm sorry, that was negative square root 3. If x is positive and y is negative, that's quadrant 4. Okay? So what's going to have a tangent of square root 3 over 1? That's going to be 60 degrees is my reference. But if I'm in quadrant 4, my theta is going to be what? 300 degrees, isn't it? Okay? So I'm dividing by R is 2, CIS 300 degrees. Okay? Now, let's write this in this form. 3 CIS 30 degrees divided by 2 CIS 300 degrees. Okay? Now, let me place this answer back up here. What I got was 3 halves CIS 90 degrees. I want to show you something here. Notice the 3 halves here. 3 halves, 3 halves. Let me write that down. And I'm going to show you something that happens here. Notice the angle up here is 30 degrees and the angle down here is 300. What happens if I take 30 and subtract 300? I get a negative, don't I? Negative 270 degrees. Think about on your XY axis, if you start here and you go in a negative direction, that's clockwise, isn't it? If you go negative 270 degrees, where are you? Aren't you in the same place as you would be if you went 90 degrees? Negative 270 degrees is equivalent to 90 degrees. Look at this answer and look at this one. Okay, so this is going to give us our rule for dividing complex numbers that are written in trigonometric form. We're going to write it in the fraction format. We will divide the r's, r1 over r2. We're going to write our CIS, and we will take the angle on top and subtract the angle on bottom. Now sometimes we will want to change the form of that angle. We may want to take out revolutions, but recall in the trig form we usually write a positive angle between 0 and 360. So I'm not going to leave this negative angle. Okay? I'm going to convert it into a positive equivalent angle. So this gives us our quotient theorem. The quotient of two complex numbers in trigonometric form is given by R1 CIS theta 1 divided by R2 CIS theta 2 equals. Notice here you have your R1 divided by R2. Sometimes that will be a fraction, sometimes it will divide evenly. Then you have your cosine plus I sine, and notice what you do here. You take theta 1 minus theta 2. Theta 1 means the one that's on top. So the angle on top minus the angle on bottom. Be sure that you do not reverse those. Remember, when you're subtracting, the order that they're in makes a big difference in your answer. Okay, so let's take a look at another example. Find the quotient and then write the answer in standard form. I have 15 cosine plus I sine 300 degrees being divided by 3 cosine plus I sine 60 degrees. Okay, well, we'll start with the r's. 15 divided by 3 gives us a 5, doesn't it? Then we're going to write our cosine plus I sine. Remember, you're going to take the top angle and subtract the bottom angle. So you want 300 minus 60. That gives you, what, 240 degrees, doesn't it? Okay? Well, let's see. Let's think about 240 degrees. Does that sound like perhaps a special angle? Well, let's see. If we go here and go around 240 degrees, 240 minus 180 is how much? 60, isn't it? So our reference angle is 60 degrees, but we're in quadrant 3. Okay? So again, I'm going to put this 30-60 triangle up here for you to look at. Alright, so this means I have 5 times the cosine of 240 degrees plus I times the sine of 240 degrees. Okay, I think I'll just write it in here and then we'll distribute the 5 later. Since we are in quadrant 3, the cosine and sine are both what? They're both negative, aren't they? Okay, so it's just like the cosine of 60, which would be 1/2, but it's negative. And then, again, the sine's going to be negative. It's just like the sine of 60, square root 3 over 2. Remember, that one is times I. So we have negative 5/2 distributing here, minus 5 square root 3 over 2i is our solution in standard form. I might want to remind you at this point, whenever you're asked to convert back over to standard form, if you have special angles or angles whose reference angles are special angles, you should always give the exact values unless you are specifically told to give a calculator or decimal approximation answer. If those angles are not special angles, then you'll just immediately go to your calculator. Okay, well, let's take a look at this next example. Find the quotient and write it in standard form. 2.1 cosine plus I sine 127 degrees divided by 7 cosine plus I sine 43. So remember, the first step is to divide your r's. Well, 2.1 divided by 7 is going to give you a 0.3. Then we're going to write our cosine plus I sine. 127, remember, you take that one first and subtract the one on bottom. So 127 minus 43 gives me 84 degrees. Now this is not a special value, is it? So 0.3 times the cosine of 84 degrees plus I times the sine of 84 degrees. And we're going to simply use our calculator. So again, I'll be distributing as I do this. 0.3 times the cosine of 84. Again, I remind you, be sure that your calculator is set appropriately. Okay, so I have here that this is approximately 0.031. Okay, and I know this is first quadrant, so that's going to be positive. Now I'm going to do 0.3 times the sine of 84. And that's going to give me a positive 0.298 times my I for the standard format. Now, a lot of times you will be given instructions perhaps on how many decimal places to keep. You might want to pay attention to that or ask your instructor on homework how many decimal places they want to stay in that answer. Find the quotient and write it in standard form. Well, you'll notice here that I have just complex numbers that are not written in the trigonometric format. So I think what I'm going to do is convert them over first of all and do the division, and then we'll come back and convert our answer back. 5, if you think about 5 plus 0i, r is going to be the square root of x squared 25 plus y squared 0. The square root of 25 is 5. If you think about the ordered pair 5, 0, your angle theta is going to be 0 degrees, isn't it? So my number on top is going to be 5 CIS 0 degrees. Okay, that one was easy to convert. For my second one, r is the square root. If I square x, I get 3. Plus, recall here, that's a coefficient of 1, so 3 plus 1, square root of 4 is 2. The tangent of angle theta is my y, which is 1, over my x, square root 3. I'm in the first quadrant, so the angle whose tangent is 1 over the square root of 3 is 30 degrees. So I have 2 CIS 30 degrees. Okay? 5 divided by 2, that's not going to be exact, so I'm going to leave that 5 halves. CIS, 0 subtract 30 gives me negative 30 degrees. Okay? Now, if I'm going to leave this in trig form, I'm going to convert that from a negative angle to a positive. So negative 30 is going to be the same thing as what? 330 degrees. The main thing, though, because I'm going to go back to standard form, is I'm in quadrant 4. Okay? So in quadrant 4, the cosine is what? Positive, isn't it? So basically my reference angle, notice, is 30 degrees. And what's the cosine of 30 degrees? It's square root 3 over 2. Now in quadrant 4, the sine is negative, isn't it? Okay, and the sine of 30 degrees is 1/2. So I have 5 halves times the quantity square root 3 over 2 minus 1/2 I. Now let's distribute. We have 5 square root 3 over 4 minus 5/4 I, multiplying that out. What we have attempted to show you here is that sometimes multiplying and dividing complex numbers is easier if those numbers are written in trigonometric form. And then if we need the answer converted back to standard form, then it's quite easy to do that. This completes our lesson on the trig form, or doing the multiplication and quotients of the trig form of complex numbers.